testing code by actually running it is, well, it's a crutch.
Oh, coming in hot today.
I really am. But seriously, if we are talking about the future of AI coding agents, the autonomous systems that are supposed to be building our software tomorrow.
Right, the AI devs.
Yeah, exactly. Relying on dynamic execution for those agents is an expensive, unscalable, and frankly, a completely dead end.
Okay, a dead end. But before we get to why you are declaring the absolute death of the test suite, let's ground this in a universal trauma.
No, I'm ready.
Because if you write code for a living, you have experienced the dependency doom spiral.
Oh, God. The doom spiral.
You know the exact feeling. You get tasked just with fixing a tiny bug in a repository that hasn't been touched in, say, 3 years.
Right.
You clone it down. You don't even want to write new logic yet.
No, you just want to run the existing test, right, just to establish a baseline.
Exactly.
Right.
And that is when the nightmare begins.
Yep.
You spend the next 72 hours fighting broken NPM packages, missing pip wheels.
A Python environment that demands version 3.7 when you only have 3.11.
Yes. And deprecated Docker images throwing cryptic C++ compiler errors.
Just because some obscure subdependency from, 2018 is suddenly incompatible with your modern kernel.
Right. You are no longer a software engineer at that time.
No, you're an archaeologist, desperately digging through the digital ruins of dependency hell. It's entirely soul-crushing. Because you just want to know if your one-line bug fix literally changing a Boolean from true to false actually works.
But suddenly you're compiling Node.jip from source.
Because some transient logging library demands it. It's ridiculous. But what if we didn't have to do that?
Well, that's the dream.
What if an AI could look at your code, understand the entire architecture of the system, and perfectly verify if your complex code patch works without ever executing a single line of that code?
I mean, that is the holy grail of automated software engineering.
So picture this scenario for a second. You have been parachuted into a massive, undocumented legacy enterprise code base.
Okay, I'm picturing it. I'm already stressed.
Right. We were talking a million lines of Java or C#. There are 0 unit tests.
Sounds about right for enterprise.
The local environment hasn't built successfully on any developer's machine since, 2023.
So everyone just pushes to a staging server and prays.
Exactly. Push and pray.
Yep.
So you find the bug, you write the fix. How do you, as a human being, actually know it works before you deploy it?
Well, you don't run it, you read it.
Right.
You start at the line you just changed, and you trace the logic backward.
You search the code base for every single place that modified function is called.
Exactly. You look at the data types of the variables being passed in, you trace the execution paths through different files, and you basically simulate the entire state of the program right there in your head.
Powered mostly by caffeine and sheer willpower.
Pure willpower. It's intense static analysis.
And this is exactly the wall that AI coding agents hit today. We are trying to build these autonomous developers, but we're forcing them to rely on fragile test environments.
Instead of teaching them to read and trace logic the way a senior engineer does.
Yes, and that specific bottleneck is what a fascinating new paper aims to solve.
The one from Shanghai Jiao Tong University and ByteDance, right?
Yep. Released just before our recording date of July 1st, 2026. It's called Dockerless, Environment-Free Program Verifier for Coding Agents.
It is such a brilliant piece of work. The core realization here is that to build truly autonomous AI software engineers, we have to stop trying to force them to build Docker containers for every single random repository on the internet.
We need them to simulate the execution in their heads.
Exactly.
So our mission for this deep dive is to unpack exactly how Dockerless achieves this.
We're going to explore how it replaces fragile test execution with a concept they call Agentic repository exploration.
We'll tear down the architecture, we'll scrutinize the benchmarks because honestly the claims are massive, and we will figure out how you can apply these exact verification principles to your own daily workflow.
Let's start with the root of the problem, though. To understand why Dockerless is a paradigm shift, we have to look at the massive bottleneck of the environment-based testing paradigm.
Okay, lay out how you actually build a state-of-the-art AI coding agent right now.
Well, you don't just train a massive language model on all of GitHub and hope for the best.
Right, that's just the base model.
Yeah, the post-training pipeline is where the real magic happens. You use 2 primary techniques. First, supervised fine-tuning, or SFT, where you show the model thousands of examples of high-quality bug fixes.
Okay.
And then you use reinforcement learning, RL, where the agent attempts to fix a bug on its own, and you give it a reward signal based on whether it succeeded or failed.
Wait, so you're telling me for both of those stages you need an absolute undeniable source of truth?
You need a grading mechanism, yeah.
If the agent generates a patch during reinforcement learning, the system has to confidently say, yes, this resolved the issue. Here is your positive reward.
Or, no, you broke the build, negative reward. And currently, the gold standard for getting that pass-fail grade is running unit tests inside isolated per repository environments.
And practically speaking, in the real world of infrastructure, that means building custom Docker images for every single repository your agent interacts with during training.
Which is an absolute logistical nightmare.
I mean, think about the computational overhead.
It's massive.
Setting up these environments dynamically means your training pipeline has to download the repository, inspect it to guess the dependencies, build the Docker image, resolve those dependencies over the network.
Figure out which test files are actually relevant to the specific issue the agent is trying to fix.
Right, and then write a custom bash script to execute only those tests, run it, and then somehow parse the raw standard output to figure out if it passed or failed.
It is an incredible amount of heavy lifting. It can take minutes or sometimes hours per repository just to get a simple binary signal of a 1 or a 0.
The compute cost alone is staggering. But there's a much more insidious problem, isn't there?
Yeah, there is. It is practically impossible to scale this approach across the diversity of real-world software.
Right.
Even the most advanced automated pipelines fail to successfully set up environments for a massive chunk of repositories. The researchers point out that this execution-based verification is completely blind to the vast, long tail of software.
The long tail, like private enterprise code bases.
Exactly. 10-year-old monoliths or legacy systems that simply lack reproducible environments or comprehensive test suites.
That broke my brain a little bit when I first read it, because if your AI agent can only learn from code that perfectly compiles in a fresh, pristine Docker container,
you are artificially limiting its training data to a tiny sanitized fraction of the actual software world.
you're training an agent that only knows how to work in perfect conditions.
You are building an AI developer that only knows how to work on the easiest 5% of modern, perfectly maintained open source projects. If it doesn't build, the agent can't learn from it because it can't get that reinforcement learning reward. The environment setup is the ultimate bottleneck capping the intelligence of these models.
So if execution is too expensive, too fragile, and ignores the long tail of real-world code, what is the alternative? I mean, obviously, researchers have tried to solve this before Dockerless came along.
Oh, they definitely have. The primary alternative up to this point has been what the industry calls environment-free LLM scorers.
Okay, like what?
A great example is the Deep SWE verifier. The premise is incredibly simple, almost dangerously simple.
Dangerously simple. I'm listening.
You bypass the environment entirely. You take the original bug report or issue description. You take the candidate code patch that your agent just wrote.
Okay.
You concatenate them into a giant text prompt, feed it into a large language model, and ask, does this code patch solve the issue described?
That sounds like a recipe for disaster. You're asking a language model to do a surface-level vibe check on a raw diff.
A vibe check is the perfect way to describe it. And here's why that methodology breaks down entirely when applied to complex software engineering. Let's use a sci-fi analogy, or fantasy, actually.
I love your analogies. Let's hear it.
Imagine you are tasked with proofreading a single chapter of a massive 1,000-page fantasy novel. I hand you chapter 42, and you see that the author changed a rule about how a specific spell works.
Okay, I see the spell change.
Now I ask you, does this change break the magic system that gets introduced in Book 3?
I would have absolutely no idea. I don't have Book 3.
Exactly.
I don't know the constraints of the world. I'm looking at a localized change without any of the surrounding context.
The LLM scorer is in the exact same position. If it just sees a diff that says, change variable X to variable Y, that looks completely syntactically valid on the surface.
Right, the syntax is fine.
But without the broader repository context, the LLM has no idea if variable Y is actually defined anywhere in the scope. It doesn't know if changing that return type breaks a function call in a completely different file 3 directories over.
It's totally blind. Surface-level diff checking is completely insufficient.
Completely.
To determine true functional equivalence, like to actually know if a bug is fixed without causing a regression, it requires deep repository context.
Yes. The verifier needs to know, is this modified function actually the one being called by the system when the bug triggers?
Right. Does this alternative implementation correctly interface with the database schema defined in another module?
You cannot answer those questions just by looking at the diff and the issue ticket. You have to actively investigate the whole code base.
Which brings us to the core architecture of Dockerless. It evaluates patches without executing them, bypassing the whole Docker nightmare.
Right.
But it does so with deep, active repository exploration.
It doesn't just read the diff, it interrogates the code base.
It acts exactly like a senior engineer reviewing a complex pull request. Let's break down exactly how it does this step by step, because the architecture is beautifully orchestrated. It operates in 3 distinct phases.
Phase 1 is question generation.
Okay, so this is a crucial departure from previous methods. It doesn't just dive blindly into a million lines of code hoping to find a mistake.
No, Dockerless takes the issue description, a reference patch if one is available in the training set, and the candidate patch generated by the agent.
And it feeds all of this into a language model.
Right, and instructs it to generate a small set of highly specific verification questions.
What kind of questions are we talking about here? Give me some concrete examples of what it's trying to figure out before it even looks at the broader code.
The paper categorizes them into different dimensions of inquiry. For example, it might ask a location-based question. Where in the repository's architecture should this fix actually take effect to ensure it catches all edge cases?
Oh, that's smart.
Or it might ask a behavior-focused question. What is the intended underlying logic of this patched code, and what data structures does it rely on?
Okay, what about testing?
It could ask about test evidence. If this fix is correct, what specific assertions or state changes would we expect to see elsewhere in the system?
Wow.
Or it might generate an edge case question. Could modifying this specific configuration parameter break the initialization of other modules that depend on it?
I really love the methodology there. It is forming hypotheses. It's identifying its own blind spots before it even starts searching.
Exactly.
Like you read a bug ticket that says user login fails on mobile, and you immediately think, okay, if this is happening, I need to know if the mobile API endpoint is using the same authentication middleware as the web endpoint. You form a targeted question.
Right. And once it has formulated those hypotheses, it moves to phase 2, parallel subagents.
This is the exploration phase.
Yeah.
This is where the system gets its hands dirty.
Yes. Dockerless takes those generated questions and dispatches a dedicated autonomous subagent for each one. And here is the kicker, the absolute plot twist.
Okay, hit me.
These agents do not run the code. They do not have a Python interpreter or a Node runtime. They are given read-only access to the static repository using standard shell tools.
Wait, so you're telling me they are literally just using bash commands? They are navigating the file system using text search?
They are using exactly the tools a developer uses in their terminal. They use find to locate files. They use grep, or more specifically our grep, which is blazing fast to search through the text of the code base.
So they're looking for where functions are defined, where they're invoked, how specific classes are initialized.
Exactly. They follow the trail of variables. They are actively gathering hard textual evidence from the repository to answer their specific assigned question.
But wait, why use bash tools like ripgrep instead of, say, embedding the entire codebase into a vector database and doing a semantic similarity search? A lot of AI coding tools use retrieval augmented generation, RAG, to find context.
That is a great question. Because vector embeddings are fantastic for finding conceptually similar code, like show me examples of database connections.
Right.
But vector math is fuzzy. When you are verifying a patch, you need absolute deterministic precision.
I see.
You need to know exactly where a specific variable named offset text is declared. A regex search with ripgrep gives you the exact line number and the exact syntax every single time. It is deterministic evidence gathering.
That makes total sense.
And crucially, these subagents run in parallel. If you have 4 questions, 4 agents, search the code base simultaneously to keep the latency as low as possible.
It is essentially sending out a squad of little AI forensic detectives into the codebase, each armed with a magnifying glass and a specific clue to hunt down.
I love that visual.
They scrape the files, find the relevant function definitions, and pull those text blocks back. Once all the detectives report back to headquarters, we hit phase 3, judgment.
Right. The subagents return their findings. They provide the original question, their text-based answer, and the raw code snippets they extracted as hard evidence.
And Dockerless aggregates all of this.
It does. It takes the original bug issue, the proposed code patch, and this newly gathered dossier of repo-specific Q&A evidence. It feeds this entire massive context window into a final judged module.
And the judge evaluates the evidence and makes the final call on whether the patch works.
It does, but it doesn't just output a simple text response saying pass or fail. The researchers did something mathematically clever here.
Ooh, math. What did they do?
In a language model, every token generated has an underlying probability score called a logit. The judge is prompted to output a specific binary token, usually representing true or false, or pass or fail.
Okay, let's define logits for anyone listening who hasn't built an LLM from scratch.
Good call. Think of a logit as the raw, unnormalized score the neural network assigns to a possible next word before it turns that score into a percentage probability.
Got it.
The researchers extract the specific logits for the pass and fail tokens. They apply a mathematical function called softmax to convert those raw scores into a continuous probability distribution. Ultimately, they map this to a continuous correctness score strictly between 0 and 1.
Okay, so instead of a rigid binary, you get a nuanced confidence metric.
Exactly.
Like a score of 0.99 means the model is incredibly confident, based on the evidence, that the patch resolves the bug.
Yeah.
A score of 0.55 means it's basically flipping a coin because the evidence is conflicting. And a 0.05 means it is highly confident the patch is garbage and will break the system.
This continuous score is vital because it provides a much richer gradient for reinforcement learning. It tells the agent not just that it failed, but how badly it failed or how close it was to succeeding.
Okay, the architecture makes total logical sense. Hypothesize, gather evidence, judge the evidence.
Simple.
On paper, sure, but an architecture is only an empty shell. It is only as good as the underlying neural network powering it. How did they actually train this verifier to be so methodical?
That's the real trick.
You cannot just take a base model off the shelf, even a smart one, give it a prompt, and expect it to flawlessly orchestrate multi-agent bash scripting detective work without hallucinating constantly.
You absolutely cannot. The prompting alone is not enough. The researchers had to explicitly train the underlying model, which in this case is a 9 billion parameter model called Quen 3.59b.
Okay.
They trained it using a sophisticated technique called rejection sampling.
Oh, rejection sampling. If you haven't built a model using rejection sampling before, think of it like an incredibly strict grading rubric applied to a massive volume of homework. Walk us through how they applied it here.
Imagine you have a student, your untrained base language model. You give the student a test. In this context, the test is an issue ticket from a known dataset along with a potential code patch.
Right.
The student goes through the entire Dockerless process we just described. They generate questions, they simulate the subagents gathering evidence using RipGrip, and they write out a final judgment. They document their entire thought process step by step.
Right, they show their work.
In machine learning, we call this documented process a trajectory.
So the model generates a massive text log of everything it did to arrive at its conclusion.
Exactly. Now, because the researchers are using specific data sets for this training phase, specifically 3,700 issues from data sets called SESWE, GIM, and MultiSOPUE, RL, they possess a distinct advantage.
What's the advantage?
For these 3,700 issues, they actually do have the Docker environment set up. They know the absolute execution-based ground truth. They know definitively if the patch passes the unit tests or fails them.
Ah, so they hold the master answer key.
Yes. In rejection sampling, they look at the student model's final judgment at the end of its trajectory. If the student guessed correctly, if its static analysis conclusion perfectly matches the actual dynamic test execution result, they keep that entire thought process.
They save that trajectory as a golden example of perfect reasoning.
Yep. If the student guessed wrong, or if its reasoning was flawed, even if it guessed right by accident, they threw the entire trajectory in the trash. They reject it.
Wait, so you're telling me they utilized the incredibly expensive, slow, fragile, Docker-based execution tests just once in an offline setting to grade the AI's homework.
That's it. Just once.
They sifted through all the attempts, kept only the trajectories where the static analysis perfectly predicted the dynamic runtime reality, and then used only those perfect papers to train the Dockerless model.
That is exactly the methodology.
That broke my brain. That is incredibly elegant.
Isn't it?
You pay the excruciating setup tax once during the training phase. And from that point onward, your model has internalized how to deeply reason through a code base. It learns the underlying logic of verification, the mechanics of evidence gathering, rather than just learning to pattern match syntax.
Exactly. It learns how to prove a patch works without ever needing the runtime environment again.
It ensures the training signal is pristine end to end. The verifier isn't just learning to blindly guess, pass, or fail. By fine-tuning on these perfect trajectories, the model is forced to learn how to reason step by step.
How to construct a logical argument based on extracted text, and how to conclude the final verdict based on real evidence. It aligns the model's static analysis capabilities with the rigorous reality of dynamic execution.
Okay, let's transition from the theory to the practice. What does this actually achieve? It is time to look at the hot takes and scrutinize the actual benchmarks. Because the claims made in this paper are massive, and we need to look at the numbers as of this paper's release in July 2026.
The quantitative results are, frankly, staggering. Let's evaluate Dockerless purely as a standalone verifier first, ignoring the agent part for a moment, just acting as a system that grades patches.
Okay, just grading.
The researchers evaluated it on the SWE Bench verified dataset. SW Bench is widely considered the gold standard for AI coding. It consists of real, complex GitHub issues that require modifying multiple files to resolve.
Right, it's not just fix this typo.
No, it's hard. On this benchmark, Dockerless outperforms the absolute strongest open-source verifier available by a massive 14.3 AUC points.
Wait, for those who don't spend their weekends refreshing ML leaderboards, let's clarify that metric. What does an 81.0 AUC actually mean in practical terms of pass-fail accuracy?
AUC stands for Area Under the Receiver Operating Characteristic Curve.
Right.
It is a metric used to evaluate binary classifiers. Essentially, it measures the model's ability to distinguish between classes. In this case, distinguishing between a valid working patch and a broken failing patch.
Got it.
A score of 50 means the model is just guessing randomly. A score of 100 means perfect accuracy with 0 false positives and 0 false negatives.
So it's measuring the trade-off between catching all the bad code and accidentally rejecting good code.
Yes. And in the world of machine learning benchmarks, researchers fight tooth and nail, spending millions of dollars in compute to secure a 1 or 2 point increase in AUC.
Yeah, progress is usually incremental.
A 14.3-point jump in a single paper is absurd. Hitting an 81.0 AUC overall proves definitively that granting the language model access to static repository exploration via bash tools fundamentally transforms its ability to evaluate complex software engineering tasks.
It is a massive leap. But the real flex of this paper, the thing that elevates it from a cool tool to a potential paradigm shift, is the end-to-end evaluation.
Oh, absolutely.
They didn't just build a highly accurate standalone verifier. They took Dockerless and used it to completely rip and replace dynamic execution environments out of the entire post-training pipeline of an AI coding agent.
Let's expand on that post-training pipeline because this is how the industry is actually trying to build the next generation of autonomous developers. We mentioned supervised fine-tuning and reinforcement learning.
Right, SFT and RL.
Historically, both of those complex stages were hopelessly shackled to Docker environments because they needed that ground truth pass-fail signal.
But the Shanghai, Tong, and ByteDance team threw the Docker dependency in the trash.
They did.
They used Dockerless as the sole gatekeeper for SFT data, utilizing it to decide which agent-generated examples were logically sound enough to learn from. And then they slotted Dockerless in as the reward model for the RL phase, grading the agent's attempts on the fly entirely environment-free.
And the resulting agent model, which they dubbed Dockerless RL9B, is an absolute monster.
Give me the numbers.
When unleashed on the SWE Bench verified benchmark, again, real-world GitHub issues, it hit a 62.0% resolve rate.
Wow.
It hit a 50.0% resolve rate on the multilingual benchmark, and an impressive 35.2% on SWE Bench Pro, which is the most brutally difficult subset.
To put a 62% resolve rate in context, this completely crushes the base model they started with, Quen 3.59b, beating it by 2.4, 8.7, and 2.9 points across those respective benchmarks.
Right.
But more importantly, when you compare it to the next best open source software engineering specialist model on the market, which is SWE Lego 8b, Dockerless RLNB beats it by over 20 absolute percentage points.
It is a profound leap in capability, but here's the most critical comparison of the entire paper. This fully environment-free model practically matches the performance of cutting-edge models that had the luxury of running actual dynamic tests during their training.
It matched them.
Yes. By utilizing agentic repository exploration, they completely closed the historical performance gap between static analysis and dynamic execution.
Which means the implications are huge. We can now train state-of-the-art AI coding agents on the tens of millions of enterprise repositories, private code bases, and legacy systems that simply do not have pristine functional CI/CD setups.
We are unlocking the dark matter of the software world, the vast long tail of code for AI training.
That is the big picture. And there is a fascinating, highly specific nuance in how they achieve these numbers, particularly during the SFT data filtering stage. It is a powerful lesson in modern machine learning that proves quality dictates outcomes far more than sheer quantity.
Yes, the SFT filtering data is one of my favorite parts of the paper, too.
Walk through those specific numbers because it highlights a major flaw in how many people train AI today.
Okay, so the researchers generated a massive raw pool of 16,000 environment-free agent rollouts. Basically, they let their base AI attempt to fix thousands of bugs, resulting in 16,000 candidate trajectories.
Okay, huge data set.
Now, conventional wisdom in the early days of deep learning was more data is always better. You might assume, great, we have 16,000 examples of coding attempts, let's shove all of them into the supervised fine-tuning pipeline.
Oh.
But when they actually ran that experiment, training the model on all 16,000 unfiltered raw rollouts actively hurt or stagnated the model's performance. The resolve rate on the SW bench verified benchmark dropped to 58.8%.
Because a massive portion of those 16,000 attempts were essentially garbage.
Exactly.
The AI was hallucinating variables, guessing at logic, or writing syntactically correct code that failed to solve the underlying bug. If you train a model on garbage, it learns to confidently produce garbage.
Precisely the problem. Raw, unfiltered agent rollouts are incredibly noisy. But then they unleash the Dockerless verifier on that dataset.
To clean it up.
They use Dockerless to meticulously evaluate all 16,000 attempts, generating that continuous correctness score for each one. They then aggressively filter the dataset down, discarding the bottom 75% and keeping only the top 25%.
So just the best 4,000 trajectories, according to the Dockerless judge.
Right. And when they trained the model on just those 4,000 highly vetted, rigorously scored examples, performance jumped up to 60.6%.
Throwing away 12,000 pieces of training data actually made the resulting AI 2% smarter.
It categorically proves how critical a reliable, high-fidelity correctness signal is. Dockerless provided a much more effective selection signal than just randomly sampling the data or relying on an LLM vibe check.
It highlights a major shift in AI development. You don't just need data, you need verified data. A strong, autonomous verifier is the ultimate gatekeeper for creating a highly capable agent.
Absolutely.
Okay, seeing all this data, seeing how profoundly powerful this static analysis architecture is, I am going to double down on my spicy take from the cold open.
Oh, here we go.
This paper is the writing on the wall.
Uh-huh.
It proves that dynamic execution is an outdated crutch. We simply don't need dynamic environments anymore.
Wait, really?
Yes. Deep static analysis, driven by parallel LLM subagents querying the codebase, is the inevitable future of all CI/CD pipelines. Think as the economics. Why would any engineering organization pay for the massive compute required to spin up a heavy Docker container, install gigabytes of dependencies, and run thousands of slow unit tests every time a developer opens a pull request, if an AI can just read the repo and give you the same highly accurate pass-fail signal in a fraction of the setup time? It's over for Docker.
Okay, I have to strongly push back on this conclusion.
Get back all you want. The numbers are there.
You are looking at an incredibly impressive optimization and extrapolating it into a magic bullet. And in doing so, you are completely ignoring the fundamental physical and epistemological limitations of static analysis.
I don't see why not. The benchmarks literally show it matching execution-based training models. It closed the gap.
Here's the thing, though. It closed the gap for training coding agents on a specific distribution of mostly logical bugs within a benchmark environment. But think about what you are actually doing under the hood.
Okay.
First, you are trading compute overhead, the cost of spinning up Docker, for a massive amount of token generation overhead. Running multiple LLM subagents in parallel, processing thousands of tokens of bash output, requires a staggering amount of GPU inference compute. It isn't free.
Fair point. Inference is expensive.
But more importantly, static analysis, no matter how advanced the LLM's reasoning capabilities become, will inevitably hallucinate when faced with complex dynamic state changes that only manifest at runtime.
Give me a technical example of something an LLM subagent absolutely cannot figure out by grepping the repository.
Okay, think about a bug that only triggers due to a highly specific race condition between two asynchronous threads trying to access the same database row simultaneously under high network latency.
Oof. Yeah, race conditions are tough.
Or consider a notoriously difficult memory leak that only occurs when a specific outdated C library interacts with a quirk in the Linux kernel's memory management during sustained heavy load.
Right.
A static analyzer is ultimately just reading the text of the source code. It cannot reliably simulate the physical reality of the hardware, the non-deterministic timing of network packets, or the dynamic state of the system memory allocation.
That makes sense.
If you feed that kind of bug to Dockerless, it will look at the code, it will try to logically reason through it, and ultimately it will blind guess because the information required to solve the bug isn't in the text, it's in the runtime state.
I see what you're saying. The bug doesn't exist in the static text.
Exactly.
If the bug relies on runtime emergent behavior, reading the source code isn't enough, because the source code alone doesn't contain the bug. The interaction between the code and the execution environment contains the bug.
Exactly. Dockerless is a brilliant bypass for the 80% of bugs that are purely logical in nature. Things like using the wrong variable name, writing incorrect control flow, misaligning API calls, or formatting JSON incorrectly.
Right, the daily grind bugs.
For those issues, deeply reading and searching the code is completely sufficient. But for the gnarly, dynamic, system-level issues, the other 20% execution is the only ground truth that exists.
So you're saying execution isn't a crutch?
No, it is the ultimate arbiter of physical reality. Dockerless just proves that we don't need to invoke the heavy machinery of physical reality just to verify a trivial spelling error in a configuration file.
That is a very solid counterargument. I concede the point. It is a massive optimization for the majority of the workflow, not a total existential replacement for runtime environments. It solves the 80-20 rule beautifully.
It really does.
So, to really solidify how this logical verification works in practice, let's walk through a mental demonstration. Let's look at exactly how Dockerless handles a real tricky bug based on the specific matplotlib example detailed in the paper.
This is a perfect example to illustrate the massive difference between surface-level diff checking and deep agentic exploration.
Picture this scenario. We have a bug ticket filed against the matplotlib library, which is a massive, highly complex data visualization library in Python.
Everyone uses matplotlib.
Right. The issue ticket states that a specific property called offset text is incorrectly inheriting the tick.color property instead of the intended tick.label color property.
Okay.
The AI agent generates a candidate code patch to fix this. It modifies a few lines in an Axis configuration file to explicitly state color mpl.rcparams xtick.label color instead of just inheriting xtick.color.
Now, let's evaluate this using the old environment-free method. A surface-level LLM scorer, like DeepSWE, is handed this diff.
And what does it do?
It sees the text changed from color to label color, but it lacks the context to know if label color is even a valid property defined in the args-params dictionary in this specific scope.
Yeah.
It doesn't know where offset text is initialized.
Right, it's just guessing based on the syntax.
Exactly. DeepSWE looked at this exact patch and assigned it a continuous score of 0.035. It confidently declared the patch a failure.
But here's the critical part. The patch actually works perfectly. If you spin up a Docker container and run the comprehensive matplotlib unit tests, it passes with a perfect 1.0.
So DeepSWE gets it completely wrong.
Completely wrong because it is operating blind. Now, let's watch Dockerless tackle the exact same problem. The process starts with the setup and question generation. Dockerless analyzes the issue ticket and the proposed patch, and it generates a highly targeted question.
What's the question?
It asks, does your patch update both the X and Y axis initialization paths where offset text is created so that the color is set correctly at creation time?
Notice how incredibly specific that hypothesis is. It didn't just ask a generic, is this Python code syntactically valid? By reading the patch, it identified that if we are changing a fundamental property of a graph axis, that initialization logic probably needs to be applied symmetrically to both the x-axis and the y-axis classes.
Exactly. Next, we move to the sub-agent recon phase. This is where the heavy lifting happens. Dockerless unleashes its parallel subagents into the static matplotlib repository.
Picture the agent opening a terminal and firing off a ripgrep command. It executes RG offset text to find every single instance where that variable is declared or modified across the entire massive code base.
Just ripping through the text.
Or it might use a pipe command like find libmatplotlib-name1py zargsgrep backstack.labelcolor to understand how that specific parameter is handled in related files.
It is literally grepping the repo. And through this methodical search, the subagent locates the exact init constructor methods for both the x-axis class and the y-axis class inside the file libmatplotlib.axis.py.
It reads those methods.
confirms that offset text is indeed instantiated there, and verifies that the proposed patch correctly modifies the color assignment in both initialization paths.
And then it extracts these specific lines of code, the actual class definitions, as hard, undeniable textual evidence.
Finally, we reach the verdict phase. The subagents hand this extracting code snippet back to the central judge module. The judge examines the original patch, examines the extracted initialization methods from the actual repository structure, and concludes, ah, yes, I can clearly see the class structures. The logic of this patch holds up flawlessly within the broader context of the Axis initialization system.
And what's the score?
The judge outputs its final evaluation, a continuous score of 0.996. A resounding, highly confident pass.
It absolutely nailed it. Deep SW failed a perfectly good patch with a .035 because it lacked context. Dockerless correctly passed it with a .996 by retrieving the context.
And the actual test execution confirmed the Dockerless verdict. Dockerless simulated the surrounding context of the code without ever needing to actually run the code.
And this demonstration highlights where most people get it completely wrong when they read headlines about this paper. People hear the phrase environment-free verifier, and their brains immediately translate that to zero context. They assume the system is just pasting a Python snippet into a generic ChatGPT prompt and asking, hey, does this look okay?
Which, as we established with the fantasy novel analogy, fails miserably on complex tasks.
The true magic of Dockerless is not that it operates in a vacuum without context. The magic is that it brilliantly replaces dynamic execution context with static retrieval context.
Yeah.
It doesn't spin up the runtime environment, but it actively, aggressively searches the repository environment. You have to actually search the repo to ground the language model's reasoning in the reality of the codebase.
That distinction is paramount. It is the difference between asking someone to review a translated sentence completely in isolation versus giving them the entire dictionary, the preceding chapters of the book, and a glossary of terms used by the author. The context makes the evaluation possible.
But every system, no matter how brilliantly designed, has its breaking point. We love a good success story and a clean benchmark, but to really understand a technology, we have to look at where Dockerless falls apart.
True. What are the edge cases? What are the failure modes of this architecture?
Let's delve into what the data shows about overloading the system. You would intuitively think that if deploying one subagent to gather evidence is good, and deploying 2 is better, then deploying 10 subagents must yield incredible results, right?
Yeah. More evidence gathered, more context provided to the judge, a more accurate final verdict. Sounds logical.
It sounds perfectly logical, give the judge all the data possible. But here is the plot twist. It actively breaks the system.
Really?
The researchers rigorously tested this hypothesis on the SWE bench verified split. They manipulated a single variable, the number of verification questions the system was allowed to generate and investigate.
Okay, what happened?
When they restricted it to 0 questions, meaning it just did the baseline surface level comparison without subagents, it achieved a 78.3 AUC. When they allowed it to ask 4 highly targeted questions, performance peaked at an 81.0 AUC.
Okay, so 4 questions is the optimal threshold.
Yeah.
What happens to the accuracy if you command it to ask 6 or 8 questions?
The performance actually regresses. When they scaled it to 6 questions, the accuracy fell back down to 79.6 AUC, and the results became increasingly erratic as they added more.
Wait, why would providing the model with more context actively make its reasoning dumber?
It exposes a fundamental limitation of the attention mechanism within large language models. When you dispatch 8 subagents, they act like overeager detectives. They bring back an absolute mountain of code snippets, file path, and function definitions.
Ah, I see where this is going.
A large portion of that gathered evidence starts to become redundant, or worse, only tangentially related but ultimately noisy. You end up overloading the judge module's finite context window.
Right.
Instead of focusing its attention on the critical initialization path of the matplotlib axis, its attention gets divided and distracted by some random deprecated test file or a loosely related utility function that one of the subagents dragged back from the depths of the repo.
So providing more than 4 questions introduces a volume of noise that actively degrades the model's ability to reason clearly. That makes perfect sense when you understand how attention works. Attention is all you need, but too much noise destroys attention. It is exactly like presenting a human jury with 1,000 pieces of incredibly dense, confusing, circumstantial evidence instead of just showing them the smoking gun.
You don't make them smarter, you just confuse them into making a bad decision.
The researchers proved there is a strict Goldilocks zone for context retrieval. Asking 2 to 4 specific high-value questions seems to be the absolute sweet spot for maximizing accuracy without overwhelming the reasoning engine.
Spot on. Now, let's shift gears to another major constraint: latency. We spent the first half of this deep dive heavily criticizing the compute overhead and the setup time of Docker environments.
Yeah, dude.
But let's be honest, LLM inference, especially running multiple subagents and a massive judge context window, isn't exactly free, and it certainly isn't instantaneous.
Right, generating tokens takes time.
This is the other major trade-off you have to accept with this architecture. The paper is remarkably transparent about their latency analysis. Let's look at the wall clock reality of training an agent. A normal agent rollout, the total time it takes for the AI to read the complex issue picket, navigate the code base, formulate a plan, and write the candidate patch takes a massive amount of time.
How long are we talking?
On average, the researchers measured this at about 2,308 seconds.
Wow. That is nearly 40 minutes of compute time just to write the initial fix.
Now, how long does it take to grade that candidate fix? A standard test execution reward spinning up the pre-existing Docker container, installing dependencies, and running the unit tests takes about 83 seconds on average.
Okay, 83 seconds is actually quite fast once the Docker file is properly configured.
The surface-level LLM, Deep SWE, is incredibly fast. It takes only 41 seconds because it is just processing a single, straightforward prompt. Dockerless, however, takes a full 180 seconds to calculate the reward score.
Wait, so Dockerless is actually significantly slower than just running the damn unit tests. It takes more than double the time of dynamic execution.
It does, because it requires heavy, sequential, multi-agent token generation. It has to call the LLM to generate the questions. It has to spawn parallel bash sub-processes to search the codebase.
Read all that terminal output.
And then it has to run a massive final judgment prompt. Generating tokens takes physical time.
So if it is substantially slower than execution, why are we hailing this as a massive breakthrough?
Because you have to look at the latency in the broader context of two factors. First, consider the silver lining of the pipeline. The agent rollout itself takes 2,308 seconds. Compared to that massive chunk of time, the 180-second reward calculation is only 7.2% of the total processing time.
Oh, I see. It's essentially a drop in the bucket of the overall multi-hour training pipeline.
Right. Second, and vastly more importantly, Dockerless works on the millions of repositories where that 83-second test execution is literally impossible because the Docker environment is broken, undocumented, or simply doesn't exist.
Ah, right. It is not about being faster than a perfectly functioning test suite. It is about making verification mathematically possible when the test suite is fundamentally broken.
Exactly.
Though I will note a potential future bottleneck here. If the underlying agent inference gets dramatically faster, say, a future model can write that complex patch in 30 seconds instead of 40 minutes, suddenly that 180-second Dockerless verification becomes the massive, glaring latency bottleneck holding back the entire system.
That is a very valid critique. It is a calculated trade-off we are making today because environment setup is so incredibly brittle. But the general trend of hardware is that token generation speeds up dramatically with every new generation of GPUs and specialized inference chips.
Yeah, compute always gets faster.
As raw compute gets faster, that 180 seconds will inevitably come down, while the human labor required to fix broken Docker files will remain a constant bottleneck.
Okay, we have covered a massive amount of ground today, from the theoretical limits of static analysis to the brutal reality of bash script latency. Let's synthesize this deep dive into concrete, actionable takeaways. What are the absolute most important concepts you need to internalize from the Dockerless paper?
Well, the primary paradigm shift is that dynamic execution is no longer the sole exclusive path to validating complex code. For years, the AI industry operated on the fundamental assumption that we had to run code in a sandbox to successfully train agents to write code.
Right.
This research definitively proves you can achieve state-of-the-art reinforcement learning and supervised fine-tuning post-training utilizing entirely environment-free static repository exploration. We can now tap into the massive dark matter of untested software.
Building on that, the data regarding SFT filtering provides a masterclass in modern AI training. You must filter your data relentlessly. The era of blindly scaling up datasets is ending. Quality massively outperforms quantity.
It really does.
Training your AI on a highly vetted, rigorously scored batch of 4,000 correct trajectories produces a vastly more intelligent agent than dumping 16,000 unfiltered, noisy rollouts into your pipeline. A strong, autonomous verifier is the essential gatekeeper for building a smart model.
Absolutely. The other critical technical nuance is respecting the Goldilocks zone of context. When you are querying complex code bases, and this applies whether you are designing an AI agent or you are a human developer, gathering more context is not always better.
Right, keep it focused.
Formulating 2 to 4 specific, highly targeted questions yields the highest accuracy. Overloading a language model's context window or overloading your own cognitive load with excessive tangentially related files actively degrades reasoning capabilities and introduces fatal noise into the decision-making process.
And that leads perfectly into my favorite takeaway from this entire paper, because it is something you can tangibly apply to your workflow in the next 24 hours.
Let's hear.
The next time you are assigned a massive, complex pull request to review at work, I want you to act exactly like the Dockerless architecture. Before you even look at the proposed diff, read the issue ticket.
Stop and think.
Stop, think, and write down 3 specific, targeted questions about what you logically expect the fix to look like and where it should mathematically live in the architecture. Then, open your terminal. Use rgripgrep or your IDE's global search function to find the answers to those questions in the codebase first.
Establish the deep context.
Verify the initialization paths. Only after you have gathered your evidence should you finally look at the author's diff. If you adopt this methodology, I guarantee you will spot subtle, structural regressions in the PR immediately that you absolutely would have missed if you had just passively read the surface-level code changes.
That is phenomenal, highly practical advice. It forces you to construct a rigorous mental model of the system architecture before you allow the author's potentially flawed code to bias your thinking. And looking at how effective that methodology is brings me to a final, slightly provocative thought. It is something not explicitly stated in the ByteDance paper, but it is a natural, perhaps inevitable evolution of this technology.
Oh, let's hear this sci-fi extrapolation. Where does this end up?
We have spent the last hour establishing that advanced AI agents, utilizing systems like Dockerless, can verify complex code by autonomously reading and exploring it via search tools much better and more scalably than they can by attempting to run it in a fragile, human-configured environment. Right now, in 2026, these agents are reading legacy code bases written by humans, optimized for human readability and human directory structures. But if AI agents are rapidly becoming the primary readers, writers, and verifiers of source code, how long until they begin restructuring and writing the code bases in a way that is fundamentally optimized for other parallel AIs to read and search rather than for humans to understand?
Oh, wow. So you are envisioning a future code base that is entirely optimized for semantic search algorithms and multi-agent ripgrep retrieval, completely discarding the concept of human readability.
Exactly.
Function names that are just cryptographic hashes of their behavior, directory structures optimized for parallel parsing rather than conceptual logic.
Yeah.
That is a wild, slightly terrifying thought. We might be actively looking at the end of clean code as human engineers define it and witnessing the birth of machine-verifiable code.
It represents a fundamental paradigm shift in defining who or what the actual audience for source code is. If the AI is writing the code and the AI is verifying the code, the human is eventually removed from the text parsing loop entirely.
Well, on that profoundly existential note regarding the obsolescence of human-readable code, we are going to wrap it up. So the next time your terminal is bleeding red error messages because a 5-year-old NPM package got deprecated and your Docker container is refusing to build,
Just take a deep breath.
just remember, you might not need to run that code ever again. The future is static. May your static analyzers be sharp, your grep commands be precise, and your dependencies strictling theoretical.
This episode is AI generated with Notebook LM, based on Dockerless. Environment-free program verifier for coding agents by Wenhao Zhang, Yuling Shi, Xiaodong Gu, Chao Hu, Chaofan Wang, Yuhua Hongting Zhu, Mengnan Qi, Zhongkua Wang Ni, Zhoujin Yu, Sujin Gao, Kai Kai, and Shilin He. Informational only, not advice.
Like and subscribe if you've been enjoying the journey. See you in the next one.